wanted to cover. Were there any questions on this last example? It was the infinite sum of 1 over 3 to the k. And what we did, we looked at the first couple of terms, generated a sequence of partial sums, and then we came up with a formula for the nth partial sum and said that the sum of the infinite series is the limit on the nth partial sum. Okay, when we came up with 1/2. Were there any questions about that? So there seemed to be some confusion about taking the limit of just the terms of the sequence versus the limit of the partial sum. Does everyone feel comfortable with the differences there? It's really important to note there is a big difference. The terms of this sequence approach 0, but the sum approaches 1/2. All right, and then we looked at a couple of more of these patterns. If we get to 10.3 today, we will show how this formula comes about in 10.3. So outside of like factoring polynomial type stuff. But all right, then we'll look at our. I think this is the last example in 10.1.
Yeah.
Yeah. So does the following series converge? If so, what's its sum? So it's the same kind of approach. Let's just start looking at some terms and then see if we can make a conclusion based off of the terms. So we'll look at maybe, I don't know, the first 3 or 4 terms.
But we're always usually good rule of thumb.
Do what?
The first 4 terms, is that usually like a good rule of thumb?
Yeah, unless it's hard to determine a pattern. But usually if there's a pattern that's easy to determine, it's going to emerge. Probably, I would say, first 4 or 5. First term, a sub 1. Notice this sum starts with n equals to 0, though. So our first term is n equals to 0. So when n equals to 0, what do we get?
Pi over 2.
Sine of pi over 2.
Oh, there's a sign out there.
Yeah. Sine of pi over 2. Which is 1. And maybe I'll put this here. This is when n equals to 0. Second term is when n equals 1. What would we get there?
Sine 9 pi.
Sine of, well, sine of,
Oh, no.
sine of 19 pi over 2.
Yeah.
So we know those pi over 2 intervals, sine is either 1 or negative 1, right? So at pi over 2, 5 pi over 2, etc., we've got 1, 3 pi over 2, 7 pi over 2. Those are negative 1. So sine of 19 pi over 2, negative 1. A sub 3, the third term, that's when n equals 2. That's the sine of 37 pi over 2, which is 1. So I guess we could keep going. There's not really a good reason to do so. Keep going. Negative 1, 1, negative 1, and so forth. So what would we say about that series? Yeah, we would say that it diverges. So the sequence of partial sums, first partial sum is just the first term, 1. The second partial sum would be 1 minus 1, which is 0. The third partial sum, 1 minus 1 plus 1, which is 1. So our sequence of partial sums would either be 1 or 0. 1, 0, 1. So since the sequence of partial sums aren't some finite value like a half or 1, it's 1 or 0, not one single value diverges. Does that make sense? Do you have any questions on that? And again, this section was an overview. We looked at a little bit of information about sequences and a little bit of information about series. In 10.2, it's all about sequences. And then in 10.3 is, and forward is where we start looking at series. Okay, so I realize you don't have that in your notes. I made a handout for this. You can reference it if you need it. So terminology for sequences. Increasing and decreasing, hopefully that's pretty straightforward. Sort of the new terminology that shows up is non-decreasing and non-increasing.
There's repetition.
Huh?
There's repetition. Or at
Supposed to be
least
getting
those
passed
examples.
around.
Yeah, right, there could be. Oh, sorry. There was extra were passes back to me, so
Oh.
I thought I had. So non-decreasing allows for repetition, right? Because it says if the next term, the a sub n plus 1 term, is larger than or equal to. So non-decreasing, well, I made that kind of large. Non-decreasing simply means that it could be increasing or constant. And non-increasing, the next term is less than or equal to the previous, means that it's non-increasing could mean that it's constant or it's decreasing.
Why is it
Non-increasing.
backwards, but
Huh?
why is it non-increasing? Oh, wait. I get it. Never mind.
Okay. And the term monotonic is probably new. It's that monotonic means that it's either non-increasing or non-decreasing. So it just, as they stated there, simply means it moves in one direction. I hope bounded is pretty self-explanatory at this point. But bounded just means that there is a limit to that sequence, right? In your homework, so it's in 10.2's homework, some of the questions will ask if the sequence is monotonic.
Did we answer yes?
Homework will ask if the given sequence is monotonic. And or bounded. What?
Say
Well,
mono or momo?
Oh, yeah, that one.
almost spring break.
Okay, so to answer those questions, just graph these. I'm not going to have you graph sequences on the exam. So for your convenience, you might already have a way to plot sequences, but for your convenience on D2L, I provided this link to the sequence plotter. So I don't know. This is the sequence 1 over n. So you can just graph it and move the slider and see what happens.
You said we don't need a graph?
Not for the exam, no. The homework does ask for graphs, so just graph them with Desmos or something.
I liked when all those dots appeared rapidly.
Yeah. So remember, these are like functions, but they're not continuous. So we just get these discrete points every time we index.
Isn't that satisfying?
So that's all you need to do with those. And so we'll run through some examples to get some of this terminology down. So I forgot to change these figure numbers. They're probably not right. The material didn't change, it's just the section changed, so it was annoying to go back through and try to relabel everything I missed. Certain things clearly. So here's just a couple of graphs of different sequences. Using our terminology, let's describe these. So convergence on this first one.
Non-decreasing.
Okay, yeah, seems to converge to 1. Here's L, the limit 1 converges to 1. And it was what? Somebody said
Non-decreasing.
Yeah, non-decreasing. Does the sequence unfold in the same direction? So we would say that this is, yeah. So we could say that this is a monotonic sequence.
Because it's moving, it's just, you're starting to get the same value over and over and over again, right? It's moving in one direction.
Yeah, yeah. Well, the direction, yeah. We're not getting the same value each time. The value's getting closer to 1, and as far as the terms go. But like this one would be whatever this value is. Let's say that's 1, then this one's 2, then this one's 2.5, and this is 3,
So what do you mean
or
by
whatever.
increasing then? Like, isn't that technically increasing in a graph?
So
Yeah, it's increasing. I mean, you could say it's increasing, but when you say that it's monotonic, you're implying, because if something's increasing, it could increase like this, it could increase like that, but either way, it's still moving in the same direction.
Okay, you said it right. If it's either non-increasing or non-decreasing, I didn't see the non.
Yeah. Yeah, so some of that terminology can be weird.
So it's just it's a more descriptive way to say that it's non-decreasing.
Yeah.
Or whatever.
Yeah.
Okay.
Right. It's a little bit more specific. And we see by the sequence itself, n over n plus 1, if we looked at the limit on the nth term would approach 1, right? Just the limit on that sequence, the limit at infinity on that sequence. This one here is monotonic, but it's, as we can see, it's divergent because the terms are getting larger and larger. They're not approaching a horizontal asymptote or a finite number. So that's an example of something that diverges monotonically. What does that look like as far as like a continuous function? Does that look familiar? It could be what?
Squared.
It could be like part of a polynomial, but when we look at the 1.5 to the n, what does that tell us? It's more like a what kind of function?
Exponential.
Yeah, it's more like an exponential function. So we'll see a lot of this type of stuff moving forward, especially in 8.2 and in 8.3. 10.2 and 10.3, sorry. This used to be chapter 8, so if you hear me say 8, replace it with 10. Just let it go. Relax. All right, here's one defined as -1 to the n over n squared plus 1. What happens when we have the -1 to the n?
The sign alternates.
The sign alternates. So the first term is down here, negative, then it's positive, then it's negative, then it's positive. So does that appear to converge?
To 0.
Looks like it's closer and closer to 0.
Right, yeah, because this one's down here, then this one's here, then it's like this, right? Converges, yeah, probably to 0. But it's, it's converging via,
Oscillating.
yeah, it's oscillations.
2 L's.
Oh, yeah. Oh, well, I didn't major in English, so I have an excuse. But,
You did no breaks today.
yeah, you're going hard. It's fine, keep me on my toes. Is this monotonic?
No.
No, because it's not moving in one direction. It's positive, negative, positive, negative.
So how would you break that?
I would just say not monotonic.
Would you classify it as bounded though?
Yeah, well, in the sense that, would we classify this as bounded in the sense that the even terms are bounded from above and the odd terms are bounded from below? How about this one? Figure 8-5. Yeah, diverges, terms get larger. Eight, 4.
So if it
Diverges.
diverges, it doesn't increase nor decrease, nor
Yeah.
decrease.
Yeah. Well, some sequences could, like if it were like a periodic function, not like sine or cosine, but a combination of sine and some other function, you could have a series that look like this.
Oh wait.
This diverges.
Something like that.
Bounded.
So it's bounded, but it's not monotonic.
Okay.
Because it's increasing then decreasing then increasing then. So this oscillates, but it is still convergent. So yeah, it just really depends on the function, which is why as we move forward, we start to come up with, we have all these different tests to determine whether specifically a series, not a sequence, converges or diverges. And there's quite a few tests actually. There's at least 7 different tests for convergence and divergence. So it's not one of those things that's like really straightforward. It's actually quite involved. What would we say here with 8-4? Diverges, right?
It's bounded.
Yeah, this oscillates first term, second term, third term, fourth, fifth, sixth, etc. All right. Any questions on that?
Would we rate that last one as bounded?
No, we wouldn't say that. Well, again, the even terms are bounded by 1, the odd terms are bounded by -1. So we could say that's, yeah, we could say that's bounded.
Because it says absolute value.
Yeah.
Or is that of the end value?
What are you looking at?
The last one.
Oh, yeah. So
All
the,
relevant values of n.
Then it would be bounded?
yeah. It would be.
Is that gonna be common with any, like, most oscillating functions?
Well, except for like, what about,
Yeah.
I mean, well, I guess as long as an even function is either positive or negative, and the odd is the opposite, I guess that would be like.
Yeah. That's a safe assumption. Okay, then, specific types of sequence that we're going to look at is geometric. A geometric sequence has the property that each term is obtained by multiplying the previous term by a fixed constant called the ratio, or R. So here's the ratio. Where the ratio is any real number, then of course what we want to kind of pay attention to is what ratios give us convergence and what ratios give us divergence. So graph the sequence and determine if it converges or diverges. So again, we could just, do this long-handed and just plot a bunch of different points, but it's highly inefficient. So we'll just plot it here. All right, so we've got these two terms. Just get a few more of these terms.
how would you graph that up on a scientific calculator?
I don't know that it would graph those. You might be able to do like,
Wait for what the X.
if you can create a table, you could indicate that its step size is 1, and then you could just come up with a table of values. Something to that effect. All right, there's our graph. Converge or diverge? Converge. Yeah. Let's see what we're going to say here. Converges. Does it move in one direction?
Yeah.
Okay, so let's say converges monotonically. What's the ratio, common ratio here for this geometric? Yeah, 0.4. Our sequences that are geometric have the form R to the n, the ratio to the nth power. So our ratio here is simply 0.4. So the connection we're going to see and make is convergence and divergence by looking at the ratio. There's an example. How about negative 0.4 to the n? What do you think that's going to do? Converge. What will the graph look like?
It's gonna diverge.
Okay, let's see. Okay, this is weird. Let me see this. This makes a difference.
What if you put 0.4 in the parentheses with the negative and leave the x out?
Just delete that. Yeah. So I don't know, you can see what's happening, positive, negative, negative, positive, negative, positive, negative, positive. Let's see, is that what we have? Yeah, negative 0.4 to the end. So converge, diverge. But it oscillates.
Because you're squaring a negative.
Negative number on X bar, negative number equal.
Yeah, so let's look at, well, let's write this out. This converges, not monotonically, but via oscillations. What's the ratio? Yeah, negative 0.4. Another way to look at that was we can look at it as negative 1 times 0.4 to the n, which is negative 1 to the n times 0.4 to the n. So the negative 1 to the n is just the thing that's causing us to change sign. We already saw what 0.4 to the n looked like. Okay, how about 1.4 to the n? Does that converge or diverge? Diverges. Let's check that one out.
Sorry.
Feel that in the table.
You're just too small.
I don't know if it's better with that or with that. I think that might be a little bit better. Okay, so that one clearly diverges. Is that monotonic? Diverges monotonically. Here the common ratio is 1.4, so we've got divergence. And the negative 1.4 to the n, converge or diverge? Diverge. Is it monotonic? No, it oscillates. Because again, this is negative 1 to the n times 1.4 to the n. All right, so then ratio here, negative 1.4, diverges. So I don't know if that's enough to determine a pattern with geometric series or sequences and what converges or what diverges. Oops. I'll just put this in your notes. but we saw the 0.4 and the negative 0.4 converges, the 1.4 and the negative 1.4 diverges. So if you had to guess, where would the ratio have to be in order for it to converge? 0 to 1. The one of them was negative though.
Yeah,
0 to 1.
Negative 1 to 1.
Negative 1 to 1. So here's for the geometric sequence. Convergence. Can y'all see that? The board's so a geometric sequence r to the n power converges if the absolute value of the ratio is less than 1. We can equal positive 1, but not equal negative 1. If the common ratio r is equal to 1, what happens? What series do you get? I mean, sequence do you get? Yeah, diverging. What does it look like?
The bounded above and below at 1.
Oh yeah. At 1. Yeah. Sorry. If r is 1, it's not divergent. As far as the sequence is concerned.
Constant?
It's constant, right? So let's look at that here. If r is 1, if common ratio is 1, what we're looking at is the sequence, 1 to the n. So their notation is like this, from 0 to infinity. And so that sequence should just always be 1, 1, 1, etc. So in terms of just the sequence, just the list of numbers, it's always 1, so it converges to 1. If we were summing that stuff, would it converge? No, so the series would not converge. The list of numbers, the sequence does converge. Okay. Out here and out here, we saw with the 1.4 to the n, for example, and the negative 1.4 to the n. Inside where it converges, the 0.4 and the negative 0.4, for example, what if r is negative 1? Okay, just
Oh, no, it oscillates.
I'll pull that back up in a minute. So if
Sum of 1 to 0.
r is negative 1, we've got negative 1 to the n, 0 to infinity. So our sequence would be what? 1, negative 1. So that diverges. It's not a single value that those terms are approaching.
But the sequence would diverge too, right? Or the series would diverge too.
The series would diverge too, because the sum, if we looked at the sum of this, if we looked at this as 1 minus 1 plus 1 minus 1, right, depending on how many terms you add up, right, you either have a sum of 1 or a sum of 0. There's actually a lot of stuff dealing with series particularly. Like we don't get into stuff like, there are particular series that it just depends on how you group the terms, whether it converges or diverges. We do kind of talk about it in passing. We'll just end there, but there's other types of series that are really, really useful for real variable calculus. Okay, so here, I'll pull this back up just in case you didn't have a chance to copy. But just again, keep in mind, this is only for a geometric sequence. We've kind of already alluded to what happens when we look at a series, but we'll talk more about that in 10.3. So basically, we just need to know, if you just remember the convergence here, then by implication, you know where it diverges as well. Do y'all have any questions so far? Another theorem is the bounded monotonic sequence. Any bounded monotonic sequence will converge. So just a brief example here with the inverse tangent. The asymptotes for tangent, inverse tangent rather, were what?
Pi over 2 to negative pi over 2.
Yeah. I don't know, whatever. So there's our bounds, the bounding the sequence, and the monotonicness, I guess. So from left to right moves in one direction. And honestly, we don't really, it's nice to know that, but we don't really do a whole lot with that.
So, but I guess would it converge at 0? Or?
Yeah, so technically, if we were looking at the, you know, like the continuous function is all of this. The proper series would be this, because we're at least starting it at n equals to 0 at the very least. And so a lot of limit stuff comes back here, where especially when we want to know, does the sequence converge? That's always a question of just computing a limit at infinity. So the limit laws for sequences are the limit laws that you've seen previous with continuous functions. Like the limit of a sum or a difference is the limit of a sum or difference is the sum or difference of the limits. Because with capital A here and capital B are just what these limits are equal to. So this part is actually saying that's the limit as n approaches infinity on a sub n plus or minus the limit on b sub n. You have a constant involved, you can pull the constant out. The limit of a product is the product of the limits. The limit of a quotient is the quotient of the limits, provided you don't divide by 0. So you might, if you're rusty on these things, you need to review limits at infinity, and with that inherently involves L'Hopital's rule as well. You can access that in section 2.5 in your textbook. And when we get to L'Hopital's, that's in section 4.7. Okay. So the limit as n approaches infinity in number 5, 2n over, or plus 1 over n. What would that limit be? Infinity, right? How about number 6? 0, you've got an n squared up top and an n cubed on bottom. Number 7, we really can't compute, but it is to remind you that the limits can also pass through these roots. So the way we're looking at that is I've got a sequence that's defined as n times n plus 1 over n cubed. Does it converge or does it diverge? We compute the limit, and then we would say that that sequence converges to 0. The terms are getting smaller and smaller if we were to write them out. In number 5, the terms get larger and larger. This 1 over n term gets smaller and smaller, but then this term is 2 times, which clearly gets larger and larger. So this is section 4.7. The biggest thing to point out is L'Hopital's rule only applies to things that are 0 over 0 or infinity over infinity. So if you get something like 0 times infinity or 1 to the infinity, then you've got to rewrite it so you can apply L'Hopital's rule to it, because it doesn't directly apply. So find the limit of ln of 1 over n over n.
As a compression.
Yeah. So that's what we're computing. We're computing what the limit as n goes to infinity on that sequence. So immediately when we evaluate that limit, what do we get?
0 over infinity. 0.
Well,
1 over natural log.
yeah, what is the natural log here? The argument is approaching 0. What does the natural log of 0 approach?
0, it's 0, right?
No. Oh, negative infinity.
It's negative infinity. So here, direct substitution, negative infinity, and the denominator is approaching infinity. So that is something we can apply L'Hopital's directly to.
Can you explain why the top goes to negative thing?
Yeah, I guess there's a couple of ways to think about it. I think the easiest way is just to remember the graph of the natural log as we get closer and closer to 0. Yeah. Okay, so we're going to apply L'Hopital's to that. And put an H just to indicate that we're using L'Hopital's. And we take the derivative of the top divided by the derivative of the bottom. So what's the derivative of ln 1 over n?
Is it 1 over n, right?
1 over n times
To the negative n to the negative 2.
times the, yeah. Derivative of natural log of something is 1 over the argument. So we do 1 over the argument, and then we multiply that by the derivative of the argument. So the derivative of 1 over n additionally is negative 1 over n squared.
Times the derivative of the inside, though, right?
Yeah, there's times the derivative of the inside right here.
Oh, I see.
Yeah. So we just have the top, and it's 1. So we've got a negative 1 over n. And that limit is 0. So the sequence ln 1 over n is a sequence that converges to 0. Do y'all have any questions on that? So these kinds of series sequences rather frequent, somewhat frequent. This is kind of the same series here in sequence at number 10. This one's a little bit more generic than the one we're working with. So maybe we should work this one because it directly applies to the previous one, just so we're saving time. And then we can come back to this one right here. Does anybody remember that one? It's not 1.
That's the natural log, or E.
It's actually E, yeah. So let's see how that applies here. A more generic one here. This limit, when we evaluate it directly, what do we get?
Was it N goes to infinity?
N goes to infinity, right?
So that's going to be 0. So it's 1 to the infinity.
Yeah. That's 1 to the infinite. And I don't know if you remember or not, but those 3 scenarios where we have 1 to the infinity, 0 to the 0, and infinity to 0, those were the most complicated L'Hopital's problems, because what it requires us to do is we've got to take something that's this exponential and ultimately rewrite it so that it's a fraction, infinity over infinity or 0 over 0. So we've got to take the 1 plus a over n to the power of bn and rewrite that as e to the b times n times the natural log of 1 plus a over n. And see here we're using, let's just write x to the y is e to the y times the ln of x. Again, if that's foreign to you, you've got to review section 4.7. But since we're computing the limit at infinity on this thing, which is equivalent to this thing, we're computing the limit at infinity here as well. So the limit at infinity doesn't affect the e, it only affects the power. So maybe off to the side here, compute the limit as n approaches infinity, b times n times the natural log of 1 plus a over n. As n goes to infinity, what would that limit be?
0.
Infinity times ln of 1 is 0, right? So this direct substitution here gives us infinity times 0. Still not a quotient, right? It's an indeterminate product. We've got to turn that into a quotient. So we talked about this in chapter, what was it, 8.9 with improper integrals. You've got to rewrite this as a quotient. So we're going to leave the ln term as it is, and then we're going to divide by the reciprocal of that other factor. So we're going to divide by the reciprocal of bn.
Wait, so this is when you're doing L'Hopital's rule?
Yeah, when it's 1 to the infinity, 0 to the 0, or infinity to the 0. That's the procedure we have to go through.
But we have to get it in that form to really apply it.
Right, exactly. Yeah, it has to be a quotient of in the form 0 over 0 or infinity over infinity before we apply L'Hopital. So this is just algebraically rewritten. Let's see what happens. Direct substitution gives us what?
0 over 0?
0 over 0. So now this form is what we're going to apply L'Hopital's rule to. So derivative of ln 1 plus a over n. we've got 1 over the argument times the derivative of 1 plus a over n, which would give us what?
It's the same thing as -1 over n squared, or negative a over n squared.
Yeah,
Nice.
negative a over n squared. And then the derivative of 1 over b to the n.
-1 over b n squared.
Yeah, negative 1 over b times n squared. Okay, so remember, after you use L'Hopital's rule, you want to simplify before you compute that limit again. So we're going to simplify this. And I suppose the easiest way to simplify would just to be multiply the top and the bottom by n squared. Maybe we could just divide that out. What do you think? What's easier?
Well,
It's about the same, I guess.
I mean, we can clean it up by multiplying the top by the
Yeah, let's do that.
bottom.
So let's just get rid of the double denominator thing, I guess. So let's multiply top and bottom by b n squared over negative 1. Simplifying, what do we get? We get
Negative ABN squared over. It'll just be positive ABN squared over.
so the n squares would go out,
Yeah.
and then we still have this right here. As n approaches infinity, what does that limit approach?
0, AB over 1, or AB over 1?
AB over 1, which is AB, because this term approaches, A over n approaches 0. So this is kind of our intermediate answer, because that was the power, that was the limit on the power of E.
Oh, right, so it's e to the AB.
Right. So the overall answer, we have to go back up here. All we've done is compute that limit. That limit is AB. So this is e to the AB.
So infinity times 0, we still have to use that L'Hopital's rule for that.
Yeah, because what it's saying is one of those factors is growing really, really large, and the other one is getting really, really small. So does the large outweigh the small, or does the small outweigh the large? Which one's essentially growing faster? Is this one getting larger and larger faster, or is this one getting smaller and smaller faster? And so when we see that, like 1 to the infinity, it's not 1. 0 times infinity, it's not 0 nor infinity. It's a finite number. So that's telling us it's actually they're growing at a comparable rate. And it's when you look at it, it's not intuitive. Any other questions on that? So let's look at a couple of these, namely going back to example, what was that, 9? So example 9 then, what would that be?
E to the n.
So let's go back here. That 1, yeah, the 1 is always there. A and B could be different numbers. So 1 plus 1 over n to the n, A and B are both 1.
So it'll be E and so it's L.
So what would our limit be? Close. But remember, the limit wasn't AB, it was E to the AB. Yeah, so the limit is E to the first. Since we've seen this in class, please utilize it. This formula right here in number 10 is definitely worth remembering. You can see it saves you a lot of work. Maybe one or two more examples just so we're sure. What's the limit as n approaches infinity on 1 plus 3 over n to the 5n?
E to the 15.
Good. So that's e to the 15.
So you're saying that form, you like that? What? Let's say the limit is gonna be like that same kind of.
Yeah.
You gotta fancy.
How about the limit as n goes to infinity on 1 minus 2 over n to the 3n?
E to the negative 6.
E to the negative 6.
Good. All right.
Got it.
All right.
Locked it.
Now you're just remembering what you said.
Yeah, right.
Okay, so the procedure that we just went through is here. I don't know how clear it is, but it's definitely like math jargony. Each one of the 0 to the infinity, 0 to the 0, and 1 to the infinity, they have these forms which we see are related to that idea when we write x to the y as e to the y ln x.
So if we run into something kind of like this, would we want to algebraically get it into that position, and then we can apply this
Yeah.
really fast?
Yeah. Other than these right here, like in number 10, like if something like that showed up on the exam, then the formula is sufficient, or either one of these, for instance. Like I'm fine with you just saying that's e to the negative 6. But other ones that are 1 to the infinity, etc., we haven't actually proved or seen, so you do have to go through L'Hopital's to do that. How about 1 over n to the 1 over n? So if you wanna try that after class or something, feel free. You should get e to the 0, which is 1. The procedure to follow, we've seen that, because that's going to give us, as n goes to infinity, it gives us 0 to the 0.
So you just have to rewrite that, I guess.
Yeah. Yeah, we'll have to rewrite this one. Direct substitution, 0 to the 0. But it's very comparable. Honestly, the one we just did in example 10 is more involved. Okay. Maybe you remember the squeeze theorem when you were dealing with limits as well. They can and do come up here with sequences. Typically, we see them in the form of like trig functions. The idea is to bound that function or that sequence in between two well-behaved sequences. So if we start off with the fact that sine 6n has to be between 1 and negative 1, and then divide both sides by, or all three rather, by 5 over 5n, we've got negative 1 over 5n is less than or equal to sine 6n over 5n.
So it's going to approach 0.
Which is, yeah. And then since we've got the function in question or the series in question bounded, we can then look at the limit of all of these. Do y'all remember that? Doing that at all? Okay, so then this limit is easy, it approaches 0. This limit also approaches 0. So since the more difficult limit, I guess, is in between, sorry, larger than or equal to 0, less than or equal to 0, that means that limit has to be 0. And the squeeze theorem only works if you can get same number on both sides. If it were larger than or equal to 0 but less than or equal to 1, then that doesn't tell you anything. I mean, it tells you it's within that window.
It's all a trig function to do it, right?
Yeah. And honestly, you know, like the reason this isn't panning out for us is if we say direct substituting infinity into here, as n approaches infinity, what is the sign of 6n approach?
It's gonna oscillate.
It oscillates, right? All we know is it's between 1 or -1 way out there. Somewhere in between 1 or -1. So in the sense of a limit, this right here does not exist over 5 over n that's approaching infinity. So normally we would say if that were like 6 over 5n, we would say, well, that's something 6 over something that's getting larger and larger and larger is approaching 0. But that's not necessarily the case because you've got something that doesn't exist over infinity. So you've just got to show your work a little bit more carefully there. Are there any other questions about that? I hope, hopefully some of this stuff is review. One thing that probably didn't talk about in Calc 1 was growth rates.
No, we did.
We did?
A little bit. Not like that, though.
So over here on the left are the slowest. Those are the slowest growing functions. To right are the fastest.
Is that something we need to like memorize?
No, L'Hopital's rule will take care of these. But this, if you can remember these, it's much, much more efficient than L'Hopital's when and if it applies. Let's see what we did. That first one. I suppose we should state maybe what's obvious, but then we can maybe look at example 8 again. But a couple of things, if particularly we're looking at the limit as n goes to infinity on a sequence over another sequence. Okay. If this is equal to 0, if that quotient equals 0, then which function grows faster?
Bottom.
The bottom has to grow faster. So if this is true, let me put this if here. If the limit of this thing equals 0, then g grows faster. n approaches infinity on that quotient goes to infinity, which one grows faster? Yeah. So really, those are the two things we primarily utilize when we utilize growth rates. But the other one is, we've seen time and time again, the limit of a quotient could equal a finite number too. So if the limit at infinity of that equals some finite number, then that means they grow. Do what?
They grow at the same time?
Yeah, they grow.
Same rate.
We would say they grow at comparable rates. Yeah, but that's exactly right. So you know the way those functions are ranked, it's it's weird because you've got powers of logarithms, then the power functions like n squared, n cubed, n to the fourth, and then you got power functions times powers of logarithms, and then you've got n to any other power. So the way we're reading that is, if this is n squared and this is n to the 2.3, then n to the 2.3 grows faster than n squared. Then your exponentials, then your factorial, then your n to the n, which is not really exponential nor a power function. Sometimes people refer to those as a tower functions, but those are the fastest growing. And for instance, the reason why we care, why it matters, example 8, where we had the limit as n goes to infinity, we had ln of 1 over n, right? That was it. Yeah. Okay. So we had to go through L'Hopital's rule. It really wasn't that involved, but nonetheless, with growth rates, which one of these functions grows faster? The bottom, n to the first power of n grows faster than any logarithm. So what does that equal to? 0. The bottom grows faster. Oops, 1 over n.
What's the difference between b to the n and n to the n?
So like b to the n, b would be, so it's up top it says it's just a positive, b is actually larger than 1. So it's a real number larger than 1. So like 2 to the n exponential like functions. N to the n could be any one of those we saw earlier, like this one, 1 plus a over n to the bn. That's, that's pretty much equivalent to one of those types of functions.
Oh, so n is take a function.
Yeah.
Okay.
You see how long this page is. Let me just, I'm going to add a new page. Just continue with a couple more of these examples. So about the limit as n approaches infinity on n to the 100 over 2 to the n.
So 0.
0. Now, if you graph that, it might take you a very long time to see where 2 to the n actually overtakes n to the 100th, but eventually it does. It might not overtake that until, 10 trillion or something like that. But what we're saying is, in the sense of approaching infinity, eventually it does overtake and win.
might be when it at 101, right? When n becomes 101.
Do what?
It might be when n becomes 101. I was going to say when n becomes a bigger exponent than 100.
Yeah, what's 2 to that power, so x to the 100.
Square.
So I mean, that's right around, what, 1.007? So we're looking, that's where in x to the 100 is larger. So if we keep zooming out, it looks like x to the 100th is larger, right? For, let's see, this. Oh, it doesn't like that point for whatever reason. Okay, that one's good. 1.03 and the output is 19.219. 2 to the x, 1.03. You see that's significantly lower, right? 1.03, that's like 2. Somewhere between 1 and 2, I think. So x to the 100, clearly larger. I'm not sure how far we have to go, but we eventually see that.
This would be like a huge number.
We'll eventually see that overtaking. All right, so it's not.
It's going to be ridiculous.
Yeah, it's an extremely large number, so don't worry about finding it. The growth rate tell us that the theorem tells us that it will eventually overtake.
So that's how you would answer it?
Yeah, the limit is 0. I think I had a couple more examples. How about the limit as n goes to infinity for n factorial over n to the n?
Oh, no.
Yeah. N to the n grows faster than n factorial. Okay, does it make sense? Got the idea? Yeah. Super efficient if and when they work. So let's just rank these A, B, C, D, and G in order of growth rates. So slowest to fastest. So what's the slowest growing function here?
C.
Which one?
Or C.
C? Do y'all agree? Involves a logarithm. Okay, then what's next? D?
No.
Yeah.
B.
Oh, B. Then Dn? Y'all agree? D sub n? Exponential? Oops. A sub n next?
A will be last.
No, A sub n is the last.
A sub n will be last. I mean, G is next.
Yeah, so what we have left, factorial versus an n to the n. So G sub n and A sub n.
So if you can memorize those.
Yeah. Yeah, and I'm fine with if you say on the exam this limit is 0 because n to the n it grows faster or n to the n wins out, whatever. So reference growth rates in some way. I'm okay if you want to justify limits that way. It's
So would you have to write it out
acceptable.
like you would say that
You can use
comparison?
logic. basically.
Yeah, you would just
Just like
something
that.
like this
Yeah.
would be fine. Or you could say n to the n wins. I don't care.
You're allowed to use logic.
Yeah. And well, actually, if you look at like the theorem that involves proving those growth rates, it's actually very involved. So someone did a whole lot of work for us. So whoever that was, thanks.
Stand on the
Appreciate it.
shoulders of giants.
Yeah. All right. Well, if you can, sometime before we get back from spring break, try to look over 8.3 because we're gonna have to 10.3. 10-3. We're gonna have to move a lot more quickly because we lost a day and a half. I hope all of you have a great break. Thanks again for showing up and doing that survey. I appreciate it.
He said what the curve was for physics.
Somebody told me it was like
Shut up.
Yeah,
It was only 3 points.
that was what somebody told me, but they might have been talking about.
There's no way, because I didn't answer a 20-point question and I got higher than an 80.
The logic is the same.
Which is 6 points higher than the first exam, since I stopped.
I stayed steady with my 86 from the first exam.
Yeah, like the A, whatever.
There's no way.
So what I'm saying is, A is fun,
I should
but
probably
B is
do
1
that.
over M, the whole thing.
He's like a wounded
B is
little
basically 0,
puppy
so 1 times 0 becomes 2.
who like wants to do well.
Say that again?
just
Because here's my A.
I don't know, I
But
thought
my
that
B is
it
1
was
over M.
not
It's like
super
0, so 1 times 0 is 0.
Like,
Is that why we get
Oh,
0?
Well, if you're gonna consider that C,
Okay, maybe
then that, you know,
try.
you couldn't say that's.
And like, I think I'm just kind of convinced
No,
that
no,
the way he's doing it is a good way.
Oh, okay. Then you would have to.
Well, yeah, I just figured that's wrong logic.
Related normal people.
With a little bit of like an Aspergery.
Well, and I did a really bad job having that conversation with him too, because I'm just kind of an offensive person.
At this
and
point,
I
you're
don't
just like
really
annoyed.
tiptoe around wounded
Your
puppies.
mess still here. What? You mess